Good afternoon to each and everyone, especially to our instructor, Dr. Raymond A. Indangan. Sir, good afternoon. So, this is the Math 304 Abstract Algebra 2 and I am Nika Isdawaling for today's reporter. So, my topic for today is all about in the chapter 15, which is the Euclidean domains. So, in definition 15.1.1, a Euclidean domain A and plus and times and v is an integral domain a and plus and times together with a function v is a function from set a divides of the set of 0 into the set of non-negative integers such that number 1 for all a and b belongs to a with b is not equal to 0, there exists q and R belongs to E such that A is equal to QB plus R, where either R is equal to 0 or V of R is less than to V of B, and number 2, for all A, B belongs to A divides the set of 0 and V of A is less than or equal to V of AB. V is called a Euclidean valuation. The next two results show that the ring integer and the polynomial ring of f of x, f a field, are Euclidean domains. By example, in 15.1.2, the ring G of integers can be considered a Euclidean domain with V of A is equal to the absolute value of A, or then A is not equal to 0. Theorem 15.1.3, if f is a field, then the polynomial ring f of x is a Euclidean domain. Proof. By theorem 14.1.2, the equation 2, f of x is an integral domain defined. V is a function from set of f of x divides to the set of 0 into the set of non-negative integers by v of f of x is equal to the degree of the polynomial of f of x for all f of x belongs to capital letter big letter of f of x divides of the set of 0, since the degree of the polynomial f of x is greater than or equal by 0, v of f of x belongs to the set of non-negative integers for all f of x belongs to the capital big letter f of x divides the set of 0, let f of x g of x belongs to f of x g of x is not equal to 0. By theorem 14.1.6, there exists q of x, r of x belongs to f of x such that f of x is equal to q of x, g of x plus r of x, where either r of x is equal to 0 or the degree of rx is less than to the degree of g of x. Hence, f of x is equal to the q of x, g of x plus r of x, where either r of x is equal to 0 or v of r of x is less than to v of g of x. Let f of x is equal to a sub 0 plus a sub 1 of x plus ellipsis plus a sub n x the raised to the power of n, a sub n is not equal to 0, and g of x is equal to b sub 0 plus b sub 1 x plus ellipsis plus b sub m x sub raised to the power of raised to m, b sub m is not equal to 0. Then f of x, g of x is equal to a sub 0, b sub 0 plus the quantity of a sub 0, b sub 1 plus a sub 1, b sub 0 of x plus ellipsis plus a sub n b sub n x raised to n plus m. Since f is a function and a sub n is not equal to 0, b sub m is not equal to 0, we find that a sub n, b sub m is not equal to 0. This implies that the degree of f of x, g of x is equal to n plus m, thus v of f of x is equal to the degree of f of x is equal to n is less than or equal to n plus m is equal to the degree of f of x, g of x is equal to v of f of x, g of x. Hence, f of x is a Euclidean domain. So that's the end of the proof. By the example of 15.1.4, any field can be considered a Euclidean domain with v of a is equal to 1 for all a is not equal to 0. The quantity of a is equal to ab inverse b plus 0. By the definition of 15.1.5, the subset integer of I is equal to a plus, or the g mod of I is equal to a plus b sub I, such that a, b belongs to integers of the complex numbers is called the set of Gaussian integers. In the next theorem, we show that integer of I is a subring of C and determine the units of integers of I. Gauss, with the first to study the integers of I, and hence, in his honor, the integers of I is called the ring of Gaussian integers. So, by the theorem 15.1.6, the ring of the Gaussian integers is subring of C. The units of the ring of the Gaussian integers are plus and minus 1 and plus and minus I. It is easily verified that the ring of Gaussian integers is a subring of C. Since C is a field, ring of Gaussian integers is of course an integral domain. Suppose A plus B I is a unit of ring of the Gaussian integers, then there exists C plus DI belongs to the ring of the Gaussian integers, such that the quantity of A plus BI and the quantity of C plus this DI is equal to 1. This implies that 1 is equal to 1 is equal to A plus BI, C plus DI is equal to A plus BI, and the quantity of C plus DI is equal to A minus BI, and the quantity of C minus DI, where the bar denotes complex conjugate. So, ang bar diri din sa ibabaw, so mo rin nagitawag nga conjugate. So, thus 1 equals to the quantity of A squared plus B squared, the quantity of C squared plus D squared, and therefore 1 is equal to A squared plus B squared. Hence, A is equal to 0, B is equal to plus and minus 1, or A is equal to 1 plus and minus 1, b is equal to 0, proving that the only units of the ring of Gaussian integers are plus and minus 1 and plus and minus I. So that's the end of the proof. By the theorem 15.1.7, the ring of Gaussian integers becomes a Euclidean domain when we let the function n from the set of the ring of the Gaussian integers divides the set of 0 into the set of non-negative integers defined by n, and a plus b I is equal to a plus bi, and the quantity of a minus bi is equal to a squared plus b squared for all a, b belongs to integer. Serve as the function v. So proof. Clearly, n of a plus bi is a positive integer for any non-zero element. A plus bi belongs to the ring of Gaussian integers. Let a plus bi, c plus di belongs to the ring of the Gaussian integers. Now, n of a plus bi times C plus DI is equal to N of AC minus BD plus the quantity of BC plus AD. I is equal to AC minus BD squared plus BC plus AD squared is equal to the quantity of A squared plus B squared times the quantity of C squared plus D squared is equal to N of A plus BI, then N of C plus DI. From this, it follows that N quantity of A plus VI is less than or equal to N of A plus BI times C plus DI. It remains to be shown that for A plus BI and C plus DI is not equal to 0 in the ring of Gaussian integers, there exists Q sub 0 plus Q sub I 1 plus I R sub 0 plus R sub 1 I belongs to the ring of the Gaussian integers such that A plus BI is equal to the quantity of Q sub 0 plus Q sub 1 I and times the quantity of C plus DI plus R sub 0 plus R sub 1 I, where R sub 0 plus R sub 1 I is equal to 0, or N is the quantity of R sub 0 plus R sub 1 I is less than to N of the quantity of C plus DI. We work backward in order to see how to choose Q sub 0 plus Q sub 1 I if such an element Q sub 0 plus Q sub 1 I exists. Then in C, R sub 0 plus R sub 1 I is equal to the quantity of A plus B I minus the quantity of C plus DI times the quantity of Q sub 0 plus Q sub 1 I is equal to the quantity of C plus DI um, times to the quantity of A plus BI times C plus DI inverse minus the quantity of Q sub 0 plus Q sub 1 I. Let the quantity of A plus BI times C plus DI inverse is equal to U plus VI, where U and V are rational numbers. Then R sub 0 plus R sub 1I is equal to the quantity of C plus DI times the quantity of U plus VI minus the quantity of Q sub 0 plus Q sub 1I is equal to the quantity of C plus DI times U, the quantity of U minus Q sub 0 plus the quantity of V minus Q sub I times I. So equals C times the quantity of U minus Q sub 0 minus D times V, V minus Q sub 1 plus C times the quantity of V minus Q sub 1 plus D times the quantity of U minus Q sub 0, then times I. Now, N of R sub 0 plus R sub 1 I is equal to the C times the quantity of U minus Q sub 0 minus D times the quantity of U minus Q sub 1 squared plus C times V minus Q sub I plus D times the quantity of U minus Q sub 0 squared is equal to the quantity of C squared plus D squared times the quantity of U minus Q sub 0 squared plus the quantity of V minus Q sub 1 squared. So hence, N of R sub 0 plus R sub 1I is less than to N of C plus DI if the quantity of U minus Q sub 0 squared plus the quantity of V minus Q sub 1 squared less than to 1. We now find an element Q sub 0 plus Q sub 1I belongs to the ring of the Gaussian integers, so that the latter inequality holds. Take integers q sub 0 and q sub 1 such that u, the quantity of u minus q sub 0 squared is less than or equal to 1/4 and the quantity of v minus q sub 1 squared is less than or equal to 1/4, then the quantity of u minus q sub 0 squared plus the quantity of v minus q sub 1 squared less than to 1, let r sub 0 plus r sub 1I is equal to the quantity of a plus bi minus the quantity of c plus di times the quantity of q sub 0 plus q sub 1I. Then a plus bi is equal to the quantity of c plus di times the quantity of q sub 0 plus q sub 1I plus the quantity of r sub 0 plus r sub 1I, where r sub 0 plus r sub 1I is equal to 0, or n of the quantity of r sub 0 plus r sub 1I is less than to the quantity is less than to n the quantity of c plus di. So that's the end of the proof. In definition 15.1.8, let R be a commutative ring with 1. If every ideal of R is a principal ideal, then R is called a principal ideal ring. An integral domain, which is also a principal ideal ring, is called a principal ideal domain or the PID. Theorem 15.1.9, every Euclidean domain is a principal ideal domain. So proof, let E be a Euclidean domain with Euclidean valuation V. We want to show that every ideal of E is a principal ideal, then let I be an ideal of E. Since E is a commutative ring with 1, it is enough to show that I is equal to EA for some A belongs to E. If I is the zero ideal, then I is equal to A E 0. Suppose now I is not equal to the set of 0, then I contains some non-zero element. Let P is equal to V of X such that 0 is not equal to X belongs to I. This is a non-empty subset of the non-negative integers. By the well-ordering principle, we find that P contains at least element. Therefore, there exists an element A belongs to I. A does not equal to 0 such that V of A is greater than or equal to 0 and V of A is less than or equal to V of B for all B belongs to I. B is not equal to 0. We now show that I is equal to AA. Since I is an ideal and A belongs to I, it follows that AA is a subset of I. Let B belongs to I. Since E is a Euclidean domain, there exists Q R belongs to E, such that B is equal to AQ plus R, where R is equal to 0, or V of R is less than to V of A. Now R is equal to B minus QA belongs to I. If R is not equal to 0, then V of R belongs to P. This is a contradiction of the minimality of V of A, since V of R is less than to V of A, therefore R equals to 0, and so B equals to QA is an element of EA. This proves that I is a subset of EA, hence I is equal to AEA. So that's the end of the proof. In theorem 15.1.10, let R be a commutative ring with 1. The following conditions are equivalent. Number 1, R is a field. Number 2, R of X is a Euclidean domain. Number 3, R of X is a PID, which means the principal ideal domain. So, proof. By the equation 1 to equation 2 follows from theorem 15.1.3. Then the equation 2 into equation 3 follows from theorem 15.1.9. Then equation 3 to equation 1, let A belongs to real numbers belongs to R and A is not equal to 0, consider R is equal to AX. The ideal of R of X generated by A and X. Since Rx is a PID, there exists f of x belongs to Rx such that I is equal to f of x. Now Ax belongs to f of x, therefore there exists g of x and h of x in R of x such that f of x, g of x is equal to a, and f of x, h of x is equal to x. Since f of x, g of x is equal to a, we must have the degree of the polynomial f of x is equal to 0, and so f of x belongs to R. Let f of x is equal to b. Now, bh of x is equal to x implies that bc is equal to 1, where some c belongs to R, thus b is a unit, and so I is equal to b is equal to R of x. From this, we have 1 belongs to I, therefore 1 is equal to AF sub 1 of x plus plus x of f sub 2 of x for some f sub 1 of x. F sub 2 of x belongs to R of x. This implies that 1 is equal to dA for some D belongs to R. Hence, A is a unit in R, and so R is a field. So that's the end of the proof. In corollary 15.1.11, G of x is not a PID or the principal ideal domain. Proof. Now, integer is a commutative ring with 1. Since integer is not a field, so the ring of the Gaussian integers is not a principal ideal domain by theorem 15.1.10. So that's the end of the proof. And thank you for listening, and God bless us all.